So this code is from our original motion activated jack-o'-lantern project, which is linked down in the description below. I'm not going to get into the details, but let's look at some of the sections. We have some configuration bits over here, and we are setting up our timers and the GP wake up that we will use to wake up our micro when there is motion. And we are doing, this is our loop, the main loop, and there is some sort of animation here for the pulsating glow on the LED. And this is where we check for the motion. And if there is no motion, and if we are at the end of our animation, that means our LED is not glowing right now. We will just turn off the LED and we will put the micro into low power mode. To turn on our LED, we are syncing current through GP2, and when we set it high, our LED actually turns off, but the default value of GP2 is 0. Every time our micro resets, it will turn on. I want to stop that from happening first by setting GP2 here. So because this micro doesn't preserve its context when it wakes up from sleep, so here we put it to sleep, and if there's some motion, it will wake up and it will go all the way to the beginning of the main method. And here GP2 will be 0 by default. That will flicker the LED. We don't want that. That's why I'm just setting it here. So here you know that there is no motion, and we put our micro to sleep. But when the supply voltage drops below 3.2 volts, our motion sensor stops working and GP3 is always high. It's not able to pull GP3 low when there is not enough voltage. So what we want to do here is to extend this condition, and if we have motion, and we probably want to check the duty here too, because we don't want this analog conversion to happen in the middle of our animation. Now here is where we want to do it. So the first thing you want to do is to turn on our analog digital converter, and then usually you need to do a channel select here, but we don't need to do it in this case, because if you look at the data sheet, so these are the channel select bits. If they are 0, 0, you select GP0, 0, 1, GP1, and 1X is for the absolute voltage reference. And if you look at this, channel select bits default to 1, 1 after any reset, and when they are 1, 1, just like this, by default, our channel is at the 0.6 volt absolute voltage reference, so we don't need to change it after reset. Now we're gonna skip that bit, so instead we will just set the go and done bit, and then you will wait until it's cleared. Just an empty loop here. Once it's cleared, that means our analog digital conversion is complete, and here we can check the value which will be stored in the address register. That's for the AD conversion result, and if this value is greater than 48, then well, we want to turn off our LED first. It will probably be off at this stage, but we want to turn it off anyways, and then we will put our micro to sleep. So before programming our micro with the software update, let's see the problem in action. I have an adjustable real wacky power supply here to simulate the batteries, which is hooked up to its battery compartment right away. I just took its guts out, and currently we are powering it with 4.2 volts. That is to simulate a nickel metal hydride pack of 3 batteries, fully charged, fully healthy. When there is some motion, the lights go on. That's what we expect, and that's how it works with fully charged batteries. After a while, the lights go off. Now let's drop the voltage a little bit, and I'm just going to drop it down to 3.6 volts. And again, it should be fine. Let's give it some motion, and it's working again. Now let's wait a little bit. It will turn off on itself when there is no motion. Now we drop the voltage a little bit further down, and our cutoff was like at 3.5 volts. So let's drop it to 3.3 volts even. Now when I drop it to 3.3 volts, there was no motion at all, and it started glowing, and at this point it's refusing to go off. The reason for that is we have our 3.3 volts here coming to our circuit board, but our LDO is also dropping around 0.2, 0.3 volts. So it's about 3 volts, and now our motion sensor stops working. It's unable to pull the motion sense line down That's why just the light keeps glowing, and it makes the situation worse because this happens when the batteries are discharged and already depleted, and then it just keeps on glowing like this. It's a good indicator that, hey, something is wrong with me, but it doesn't help with over discharging the batteries. It quickly damages the batteries that are already at the end of their lives. Now I'm going to disconnect everything, take the PCB out, program it, and see how it works. Alright, so I have programmed our micro and connected our power supply to its battery compartment. All seems to be working now. When there is motion, the light goes on. When there is no motion, let's wait for it. LED goes off. Motion. Yep. And LED turns on again. So what we are going to do now to simulate this low battery situation, we will just drop the power supply voltage to, let's start with 3.6 volts first. I imagine everything will be fine in 3.6 volts because the maximum dropout on our regulator is 0.3 volts. So that should give our micro a good 3.3 volts to work with. Everything should be fine. Yeah, it looks pretty good. Then there is motion. The light comes on. When there is no motion, it turns off by itself. Now, below this point is we want our cutoff to happen. So we will go down to 3.3 volts now. This is where our batteries would be depleted, and it started glowing right away. There's a bit of an interesting spot here. Now our motion sensor stopped working properly, but we still haven't reached our cutoff voltage. So if you go a little bit lower at 3.2 volts, it should stop working completely. At this point in time, no matter what we do, there is motion or not, it should not work. This is where our over-discharge protection kicks in, and the device will stop working. One thing that I want to do before wrapping it up is just to check the current consumption at this state. I'm just going to connect my multimeter between the power supply and the battery compartment to see where we are at the current consumption. So yeah, it looks pretty good. It's around half a milliamp, and that's good enough to give batteries a little bit more time before we replace them. And that's well within the specs of our regulator and the current consumption of our micro in sleep mode. So that's pretty much all to it. Let me know if you have any questions, and check out the sample code down in the description below. It's XC8 code for PIC10F, I know, but these concepts we talked about and this method can be used with a whole bunch of different micros as long as they have an internal fixed voltage reference. Thanks for watching my video and hope you found it useful. See you next time.